Hello and welcome to this final video in our unit on probability theory. Today we are going to be talking about special random variables. So this is going to wrap up our extremely brief unit on probability theory by covering some of the distributions and variables that you are most likely to see when you are either reading through the literature for AI systems or deep learning papers, or you're trying to implement and apply these systems and algorithms to your own data. So these are going to be very important distributions to cover because I can guarantee you that you will see them or run into them or use them very quickly or eventually in your research or work. Alright, so let's go ahead and get started. A special random variable, in this context, I'm simply defining it as any distribution that is commonly found in real life data, like the Gaussian or normal distribution, or in machine learning applications like the exponential distribution. So there's two different options here. Either the distribution is often found in real life data, nature models these distributions well, or it's commonly used in machine learning applications because it has certain properties that are favorable for AI and deep learning. So the distributions that we're going to cover today are the Bernoulli distribution and the multi-Bernoulli distribution. Those are going to be our two categorical distributions that cover discrete variables. Then we also have the Gaussian distribution, which is also known as the normal distribution. This is going to be the most common of all distributions that we cover today. And we're also going to cover the exponential and Laplace distributions as well. And those last three, the Gaussian, exponential, and Laplace, those are all for continuous variables. The first two are going to be for discrete variables. So let's go ahead and start by discussing the Bernoulli. Alright, so the Bernoulli distribution is a distribution over a single binary random variable. So this variable is binary. It means it has two states. It's going to have state x equals 1 and state x equals 0. And this distribution is parameterized by the parameter phi here. So the probability of x equal 1 is going to be phi. And then on the flip side of that, when the probability of our other state, x equals 0, is going to be 1 minus phi. So we have a discrete variable. It only has two states. It's definitely not continuous. And those two states, the probability is given by phi and 1 minus phi respectively. So that's the Bernoulli distribution, and it can quickly be expanded to the multi-Bernoulli distribution. So the multi-Bernoulli distribution is a distribution over a single discrete variable with k different states. So now instead of just having a binary variable, we can have k number of states. However, k has to be finite here. K cannot be infinite, in which case we would have a continuous variable. If k is finite, we still have a categorical variable, we have a discrete variable, and we can describe it using simple probabilities for different states. So this is also known as a categorical distribution. The Bernoulli distribution is also technically a categorical distribution since it covers a categorical or discrete variable. However, you're more often to hear categorical distribution referring to the multi-Bernoulli because oftentimes we're going to have multiple states or a k number of states. So both the Bernoulli and multi-Bernoulli distributions model discrete variables where all states are known. The only difference is that the Bernoulli only deals with two states, whereas the multi-Bernoulli has k possible states. These are going to be your two most common categorical distributions or distributions that you use for discrete variables. And they may seem easy or straightforward, but the Bernoulli and multi-Bernoulli distributions are actually sufficient to describe any distribution over their domain. And this is not because they are particularly powerful, but rather because their domain is so simple. So they model discrete variables for which it is feasible to enumerate all the states. When dealing with continuous variables, there are uncountably many states, an infinite number of states, so any distribution described by a small number of parameters must impose strict limits on the distribution. Thus, the multi-Bernoulli and Bernoulli are powerful not because of their complexity, but because of the simplicity of the domain that they are covering. Alright, up next, let's move to the continuous variables. We have the Gaussian distribution, and this is actually the distribution that we explored a little bit when we were doing our R programming project. And this is the most commonly used distribution over real numbers. And as a result, it's known as the normal distribution. Gaussian and normal distributions are going to be identical distributions. And it's defined by two parameters here. We have mu and we have sigma. Sigma squared is actually what is going to be used in the actual formula. Mu here is going to be the mean. It's going to give us the central peak. The maximum is going to occur at x equals mu. And then sigma is going to be your standard deviation. Sigma squared is known as the variance. So if you take the square root of the variance, you're going to get the standard deviation, as we mentioned in earlier lectures. So first, many distributions we wish to model are truly close to being normal distributions. The central limit theorem actually shows that the sum of many independent random variables is going to be approximately normally distributed. So this means in practice, when we're going to apply these algorithms, many complicated systems can be modeled well as normally distributed noise, even if the system can be decomposed into parts with more structured behavior. So the Gaussian distribution is used all the time because nature uses the Gaussian distribution all the time. It's normally distributed. So as we mentioned, we have the mean. The mean is going to be mu. When you run across these distributions in a paper, you're going to get the mean and the variance are often going to be reported. So sigma squared here is our variance. You might hear something like a normal distribution with mu equals this value and variance equals this value, something like that. It might be reported just in the mean and variance, a distribution with mean and variance. If you hear somebody just drop off what type of distribution it is, it's often the normal distribution or Gaussian distribution as well. So let's take a look at what this looks like. As I mentioned, you have the maximum at x equals mu, and then inflection points are going to actually occur at x equals mu plus or minus sigma. And if you've dealt with Gaussian or normal distributions at all, you might hear the 68, 95, 99.7 rule. And this rule means that 68% of the data is going to be contained within one standard deviation of the mean, or mu. 95% of the data is going to be contained within two standard deviations. And then 99.7% of the data is contained within three standard deviations from the mean. So that's the 68, 95, 99.7 rules. So you actually see pretty quick from this rule, if you have a value that's 4 standard deviations away from the mean, there is a very small chance of that value occurring. However, within plus or minus 1 standard deviation, you're going to get a value 68% of the time. So this is the normal distribution. This is what it looks like. Just a nice bell curve, also called a bell curve. And you are guaranteed to see and use this when you are applying and using or developing these algorithms. All right, next is the exponential distribution. So oftentimes in AI systems, it's very beneficial to have a distribution with a sharp point at x equals 0, and that is exactly what the exponential distribution gives us. It's going to have a sharp point at that value x equals 0 and then be decaying exponentially everywhere else. So the Laplace distribution is going to be exactly the same as the exponential distribution. However, now the sharp point doesn't have to occur at x equals 0, so the Laplace distribution can give us the same exponentially decaying distribution with a sharp point at x equals mu. So instead of x equals 0, we have any value x equals mu. Mu here is not the mean, it's simply whatever value we want this peak to occur at. So the exponential distribution uses the indicator function, that's the bolded 1 with x is greater than or equal to 0, to assign a probability of 0 to all negative values of x. So in the exponential distribution, all negative values of x get a probability of 0. And then with the peak at 0, it'll be exponentially decaying after that. And then in the Laplace distribution, as mentioned, we simply have a sharp peak of probability mass at an arbitrary point mu. And again, mu here, not the mean, just whatever point we want that sharp peak to occur at. So you'll see exponential and Laplace distributions fairly often, not as commonly as the Gaussian distribution, but these are two distributions that don't necessarily occur as much in nature, but do occur often in machine learning type research. Alright, so that's just a brief coverage of some of the variables and distributions that you're going to see, and this actually brings us to the end of Unit 3 on probability theory. So congratulations for making it through the couple of lectures. I hope you learned a lot. It's not necessarily covering too much detail, but hopefully giving you topics that you could dive into more on your own time if you so desired. So thank you very much for listening, and have a wonderful day.